So after that we talked about stability, we are now going to talk about performances. The scheme that we're going to study is this type of scheme. So a scheme in which we have a controller, C of Z, in the discrete time domain. Then we have a sampler and a whole device and a plant, P of S. And after the plant, we have another sampler, and we want to study the performances of this closed-loop system. The first performance criterion is actually stability, the stability that we have already discussed in the previous lecture. So to assess if our closed-loop system is asymptotically stable or not. Obviously, that is the first step, the most important property. If our system is not asymptotically stable, then the response will diverge, will go to infinity, and our system will blow up, okay? So what we want for sure is, first of all, stability, and we call that type of stability nominal stability, okay? The reason why we call it nominal stability is to distinguish it with a different type of stability, that is robust stability. So robust stability is the first, if we want, type of performance after stability, nominal stability. So in robust stability, basically the stability properties of the closed-loop system should be preserved also when there are some perturbation of the plant. Okay? So what does it mean, perturbation of the plant? It means that the model that we have of the plant is obviously an approximation. The model is a mathematical description of a physical system, and obviously there will be differences, okay? Some disturbances, computation of parameters, some things, some forces or some conditions that we didn't consider in our model. For instance, time delays between when we give the input and when the system will produce an output. So there is a whole series of approximations that we have made from going from the physical system, to the model, the mathematical model. So it means that our model is actually not a perfect representation of the physical system. So this means that the model that we are controlling is actually a perturbation of the real model. And if we produce a controller that makes our model, our closed-loop system with our model asymptotically stable, the question is the real plant, the physical plant, asymptotically stable as well? So to answer this question, we actually study robust stability. Robust stability is basically the stability in which, instead of being happy with having poles inside the circle, we want a certain stability margin. So let's look at this example, okay? In this example, we have two poles that happen to be quite close to the unit circle. And these are the poles that have been obtained, so this is the poles of the closed-loop system. Now, what happens if our plant is actually a bit different from what we thought? So what happens is that it's possible that our pole does not actually happen at this point, but it may happen in any point inside this little circle. And it may actually happen to be here, okay? So since we don't have a perfect knowledge of our physical system, we think that here the poles are inside the circle, but actually the poles happen outside the circle in the real system. And the system is not stable. So to avoid this problem, we use a stability margin. So what we do is that we put a circle inside the bigger circle, okay? And now our control objective is not to put a pole inside the circle 1, but is put all the poles inside this smaller circle, okay? So when we do the control, we will obtain two poles here, for instance. Now, again, it's true that our model is not a perfect representation of the physical system, and so it may happen that the pole actually happen to be outside this small circle. However, since we have this margin, the overall system is still asymptotically stable. So this is the basic idea behind the robust stability, and this is one type of stability margin, a type of stability margin that is visible on the root locus of the system. But this stability margin can also be, a similar stability margin can be used when we control the system using the frequency response. Okay, so that will be a margin in the frequency domain, like for instance a phase margin. So this basically means that robust stability is more or less the same as nominal stability for what concerns this course, in the sense that, okay, instead of trying to put all the poles inside one circle, we want to put it inside a smaller circle. Obviously, the techniques are more or less the same. We just have to modify some detail. So we're not going to spend much more time on robust stability, because the discussion that we have made on nominal stability can be directly extended to robust stability. The next performance that we introduce is the steady-state accuracy. So the steady-state accuracy is concerned with the response of the system when a large amount of time is passed, okay? And we want to see how the system is behaving. In particular, we want to see if, given a certain reference, the response of the closed-loop system is a steady state following that reference or not. Okay? Let's look at an example. Okay, so we look at this example over here. So here the reference is the step unit. Okay, so we have a reference that is constant to 1. And then there are different ways the system can behave. Okay, one way is that our system is actually approaching the reference. And so we said that the steady state of this system is actually equal to 1. So we have perfect accuracy in steady state. Another case is that the system becomes constant, but the constant is actually different from 1. So we see that there is a constant error between our response and the reference. So there is a steady state error that is constant. But it's also possible that our system is diverging, okay? And then it means that the error actually between the response and the reference is growing unbounded. Okay, so the error, the steady-state error in this case is going to infinity. So I want to point out that, as I said in the previous lecture, if the system is asymptotically stable, then this case is impossible because the input of the system is bounded. So the steady-state accuracy is concerned with how the steady-state response behaves, in particular with respect to a reference or with respect to disturbances. Okay? Then a fourth aspect is the transient response. Okay? So what is the transient response? The transient response, so we can imagine to divide our response in two parts. This part is for small k, and this part is for large k. Okay, when we are in large K, we are in steady state, okay? A long time has passed, and the system reached its steady state. Instead, at the beginning, okay, there is a transient response. A transient response is a certain behavior that is going to actually decrease to 0, okay? Because we can always write the response of the system, okay, let's use K, as the sum of a transient response and a steady state response, okay? So every response can be written always as the sum of a transient response and steady state response. This response goes to 0 as k goes to infinity. This response instead does not go necessarily to 0 as k goes to 0, okay? To understand better what is this transient response and steady state response, let's look at this example. So here we have a response of a system. So we see that this response starts from 0 and converges after a while to 1. So this is actually the sum of two responses, a transient response and a steady state response. The transient response starts from -1 and converges to 0. And the steady state response instead is just constantly equal to 1. So we see that if we do the sum of these two responses, we actually get back this response. And we see that this response is the response that converges to 0, and this response is actually the response of the system after a long time of behavior. Okay? So this is basically the explanation of what transient response and steady state response is. And what we have here on this graph is that up to this point we have talked about the behavior for large values of k, so steady state accuracy, but there is also a condition we may also want to assess the performance with respect to the transient. And so we see that the transient is what happened for small values of k. Why this is important? Let's say that our response, okay, is the response of corresponds to the temperature of a certain device, okay, and we want that the temperature of this device reaches this value that is 1, that is our reference, okay. But our device is actually very sensitive, and if we go over 1.1, the device will break, okay. And we see then that what we want is that we never cross this line, okay? So this line corresponds to the point 1.1, okay? And if we cross this line, then the device will break. We see that in this case, even though we have good steady-state accuracy, we are crossing this line when we are in the transient behavior. So our transient is not good enough for our system. Okay, we have to design a new control system that assures us that our response will always be below 1.1. A possible solution is that we produce a controller that makes the system move slower, so it reaches basically the 1 much slower. Okay, so that the overshoot will be small. So this is basically the idea then to try to solve this problem. The point here is just that in addition to steady-state accuracy, we are also interested in the transient response behavior, and this corresponds to maintaining, so respecting specific bounds like the one that I just shown at the board, or in terms of overshoot, so the overshoot does not have to be too big, or settling time in the sense that the transient response has to be quick enough. Finally, the last performance that we will study is actually the performance with respect to disturbances. So we want that the effect of some classes of disturbances is made as small as possible. So let's say that, for instance, our output is measured by a sensor, but this sensor produces also a certain error in our measurement. What we want is that this error, this disturbance, does not affect the overall performance of our system. So in this lecture, we are going to cover these topics, and we are going in particular to cover only these 3 topics because we have already covered stability in another lecture. And for what concerns robust stability, we actually we are just happy about the classical stability plus a certain margin. So the techniques are basically the same. So what we are going to cover now is the steady-state accuracy, the transient response, and the disturbance rejection. So we start with the steady-state accuracy, and we consider this scheme. We consider the whole device, and for simplicity, we assume that the whole device is at 0 order hold. Okay? So the discrete time description of the plant then becomes HP of Z, okay? Because we know that when we compute the Z transform of this system over here, that's correspond to the Z transform of H0 of S times P of S. And we can use the properties of the Z transform that we already seen, and we know that this Z transform is actually equal to 1 minus Z power minus 1 times the Z transform of the plant divided S. Okay? So we call this Z transform, for simplicity, HP of Z. And then we see that the direct loop, the direct branch is C of Z times H of HP of Z. And we call this direct loop G of Z. And then we see that the error is actually given by this transfer function over here. Then what we will do in the next slides is to consider some classes of references and see how the system behaves for these references. The first reference that we consider is the unit step. Okay? So we consider as a reference a unit step, and we want to see under which condition the system, the response of the system, will achieve steady state accuracy for this reference. So let's look at this analysis. Here we have that r of k is equal to 1, okay, so this is our sequence, and we can compute the z transform of this, and we obtain this value here. Then what we want to compute is the steady state error. How do we do that? Well, we have seen that E of z, as is written on the slide, is actually equal to 1 over 1 plus g of z times r of z. Okay? Now we want to compute the steady state error. So we want to compute the limit with k that goes to infinity of E of k. But we see that we can use the final value theorem to compute this limit. So if we use the final value theorem, this is actually equal to the limit with z that goes to 1 of 1 minus z power minus 1 e power z, e of z. Okay? So we have used here the final value theorem to compute this value here. So let's go back to the slide. We want to compute the steady state error, so the value of this sequence at infinity, and to compute this we use the final value theorem, and we have this expression over here. We replace E of z, okay, and what we obtain is the following expression, okay, and we replace also r of z, that is equal to this expression over here. Now we simplify this term with this term, okay, and what is left is just the limit with z goes to 1 of 1 over 1 plus g of z. Now let's call k of p, kp, the limit with z goes to 1 of g of z. Then this limit is actually equal to 1 over 1 plus kp. And we call kp position constant, okay? Then what we notice is the following. If we want that the error is a steady state equal to 0, we see that this is possible if and only if kp is equal to infinity, because the steady state error is 1 over 1 plus kp. If we want that this fraction is equal to 0, then kp has to go to infinity, so because then we have 1 over infinity. This can happen only if this limit is equal to infinity. Now here we have a fraction, okay, and we want that when z goes to 1, this fraction goes to infinity. To do so, we have to have a division by 0, okay? So this means that g of z has to have at least one pole in z equal to 1. Why? Because if g of z has one pole in z equal to 1, when we compute this limit, then we are dividing by 0 and kp will be infinity. Kp will be infinity, 1 over infinity will be 0, and the steady state error is equal to 0. We introduced the definition of type of the system. So the type of the system is determined by the number of poles of the open loop transfer function at z equal to 1. Okay? So if g of z has one pole in 1, then the system is of type 1. If it doesn't have any pole, the system is of type 0. If it has two poles in 1, then the system is of type 2, and so on. Okay? So this basically implies that the steady state error for constant references is 0 if and only if the system is of type at least 1. So let's look back at the board, and we consider the system, this response here, that is converging to 1. So obviously, what is the steady state error between this response and 1? Is 0. So this response is the response of a system that is of type 1. Then let's look instead of this other system that is converging to this line here. What is the error? The error here is a constant. Okay? If we look back at the slide, we see that the error, the steady state error, is a constant for kp equal to a constant. When kp is equal to a constant, when g of z does not have any pole in z equal to 1. So if the system is of type 0, then we are in this situation in which the system converges to a constant. And what happened for this system over here? Well, this system over here is impossible, because this system, we said that is asymptotically stable. We say that the input is bounded, then the output cannot be unbounded. Okay? I also want to point out that if the system is not asymptotically stable, then also these two errors will not be constant. Okay? There will be not steady state. Okay? Steady state exists only if the system is asymptotically stable. We look now at the next case. The next case when the reference is instead growing linearly with k. So r of k is equal to k. We compute the Z transform, we obtain this expression, and then we do exactly the same analysis as before. We compute this error. So this is the steady state error with respect to this reference. We replace everything, and from here maybe there is a passage that is not clear from going from this limit to this limit, so maybe I can do it at the board. So we are in this situation. First of all, we simplify this term and this term, okay? Then we do this multiplication, so we have the limit with z goes to 1 of t z power minus 1 divided, and then we have 1 minus z minus 1, and then we have plus 1 minus z power minus 1 times g of z, okay? Now, since we are computing the limit with z goes to 1, we see that this does not play any role because this would become just 1. So this is actually the limit with z goes to 1 of t. We can forget about this times 1 over here. And here when we replace 1, 1 minus 1 is 0, so here we will have 0, and what is left is only this, because this is what is actually mattering. Okay? So we have this limit here. So we go back to the slide. This is what we have on the slide. And so we define kv as our velocity constant. And we see that then the error is defined as 1 over kb. Again, the error is finite if and only if kv is a number that is different from 0 and is different from infinity. Okay? So if it's just a constant that is different from 0 and different from infinity, then what happens is that here the error will be 1 over this number, and it will be a number, so the error is finite. And when this happens, so when kv is a constant, well, kv is a constant when gz has a pole in 1, so that it will cancel out this term over here, and the result of this limit will be a constant. So this means that g of z is of type at least 1. Okay? How instead we have that the error is equal to 0? The error is equal to 0 when 1 over k is equal to 0. So k has to go to infinity. K goes to infinity when this limit goes to infinity. So it means that we have to have at least 2 poles in 1. Because if we have 2 poles in 1, one will simplify this, and then there will be another pole in 1 that when z goes to 1 goes to 0. Since it's a pole, the result of the limit will be infinity. And so 1 over infinity will be 0. So the steady state error is 0 if the system is of type 2. What happens if the system is of type 0? Well, if the system is of type 0, g of z does not have any pole in 1, and when we compute this limit, since there is this 0 in 1 over here, kv is equal to 0. So we have 1 over 0, the error becomes infinity. So let's look at this case at the board. So we have our reference that is a ramp. Okay, just to point out this, I think it's obvious, but I often sketch continuous lines. Obviously, these should be interpreted as sequences because we are in discrete time systems and discrete time. But it's much easier for me to sketch that just continuous line. So we are in discrete time. So we have, this is the reference, it's a ramp. So a system of at least type 2 will behave in this way. So it will converge to this ramp. A system of at least type 1, so of type 1 actually, will actually behave in this way. And so we see that then what happens is that this error becomes constant, so it's always the same. Okay? And a system of type 0 instead will have an error that is continuing to grow. Okay? In the next slide, we study the next type of reference, and that is the parabola. Okay, so this is the type of reference. The analysis is exactly the same, so I'm not going to comment on this. We get similar expressions. We define the constant, the acceleration constant, and we have that the error behaves in this way, and obviously what we obtain is that the error is finite if the system is of type at least 2, and the error is 0 if the system is of type at least 3. Okay? And this analysis can be extended to any type of polynomial reference, and we obtain this table. Okay? So we see that the error, the steady-state error, will be the following, depending on the type of the system and on the type of reference. Okay? If the reference is the unit step, then for system of type 0, we have a constant error, and for system of type greater than 0, then we have a 0 steady-state error. For ramp inputs, ramp references, then we have this situation, and so on. And you see how this table can be extended. In the next slide, what I want to talk about instead is the transient performances, okay? So the transient behavior. So the characteristic that we can look at when we talk about the transient behavior are various. So there are different characteristics. And here I'm going to define a few of them, okay? So let's look at this slide and look in particular at this response, okay? So this is the response of a system that has a certain steady state at 1, okay? We see that the steady state accuracy is that the steady state error is actually 0, okay? Now we look at the transient part, so at this part of the graph, and we ask ourselves how we can assess the behavior, how well the system is behaving. So one thing that we define is TD over here. TD is defined as the delay time. Okay, the delay time is the time that is required to reach half the final value the first time. Okay, so the final value of this response is actually 1 in this case. In general, will be a certain steady state. Okay, the first time that you reach that final value happens over here. You see, so it's the first time that you reach that value. You will not stay there. It will continue to evolve, but it's the first time that you reach that value. That half of that time is called delay time. So the delay time is telling you basically how fast is your system to grow towards the value that you want to reach. Okay? Another measure of how fast is your system is the rise time. So the rise time instead is defined as the time required to rise from 10% to 90% of the final value, okay? So rise time and delay time are very similar to each other, okay? Are two different ways to assess how fast your system is growing, okay? I want to point out that rise time is defined in different ways, depending which book basically you read, okay? So it may be from 10 to 90%, from 20 to 80%, and so on, okay? So another important indicator is the maximum overshoot, okay? So the overshoot is the fact that the phenomenon of overshooting is the phenomenon that the system, the response, is actually overshooting your final value, the final value of 1, is going up, and then it will come down, okay? But there is this moment in which, this period in which the system is actually going up, and it will reach a maximum value. As I said before, maybe we want that the response of the system never reaches a certain high value. So we may want to put a limit on the maximum overshoot. So the maximum overshoot is basically defined as the maximum peak value of the response measured with respect to unity, if the steady state is the unity. If the steady state is not the unity, then we can define the maximum percent overshoot, that is defined as the difference between the overshoot and the value of the steady state divided the value of the steady state times 100, okay? So that we can compute this percentage when the steady state is not actually 1. What is then the next criterion? Well, the next criterion is the peak time. The peak time is the time at which the overshoot happens, okay? The last indicator that we define here is the settling time. So the settling time is the time necessary for us to decide that the system reached the steady state. Obviously, steady state is something that is reached at infinity, but in practical terms, we cannot wait at the end of the universe to say that we are in steady state. So we define the settling time in the following way. We consider a certain range around the steady state value, and this range usually is basically a 2% tolerance, so a 2% over the value and 2% lower the steady state value. And the settling time is defined as the time that is necessary for our system to enter this range and not exiting anymore. So for instance here, the response is entering this range, and since it does not exit anymore that range, this will be the settling time. This is not the settling time, even here we are inside that range, because here we are going out of that range, okay? So that's how the settling time is defined. So these indicators are basically all indicators that are useful for assessing the transient behavior of our system. Among these, there are some of these that are more important, and these are the rise time, the maximum overshoot, and the settling time. The reason is that these are obviously very important indicators because the rise time, it tells you how fast is the system responding. The maximum overshoot is telling you how much you are going over the limit that you want to achieve and possibly break the system. And the settling time is telling you when you finally reach steady state. So it's possible to produce a control system that achieves specific rise time, maximum overshoot, and maximum settling times following some specific techniques. For instance, doing control in frequency, as we will see, allow us actually to set these properties, in particular the properties of maximum overshoot. The settling time instead is mostly decided by the sampling time, okay? So the sampling time of our discrete time system has an important role in deciding the settling time in discrete time, okay? So in the previous lecture we have covered stability, we have now covered steady state accuracy, and we have talked about the transient response. Now the last topic that we cover is the disturbance rejection and attenuation. So let's consider this case. So in this case we have a discrete time system in which we have a controller C of Z and the plant P of Z. In this scenario we are assuming that there is a disturbance between our controller and our plant. Okay, so we have our controller, we have our plant, but there is some sort of disturbance. There may be, for instance, a disturbance in the electrical signal. It may be a numerical approximation when we go from discrete time to continuous time, or it may be a disturbance in how the input is actually applied to the plant because it's not correctly modeled, and so on. Okay, so we imagine that there is this disturbance, and we want to see how this disturbance is actually affecting the behavior of our system. Okay, so to do so we have to compute the transfer function between the output and this disturbance. For simplicity in this analysis, we assume that the reference is 0. Okay, if we put a reference different from 0, the analysis becomes more complicated. Obviously, the analysis can be extended to when the reference is different from 0. Okay. So let's consider the reference equal to 0, and then we compute the transfer function of the system between y and d. Okay, so this is the disturbance. So we solve this block diagram, and we find that the transfer function between y and d is given by p over 1 plus c times p. Then what we note is the following. Let's assume that the gain c times p is much greater than 1. So what is the gain? So to explain what the gain is, let's look at this example. So we have the controller, and for simplicity we assume that the controller is like this, but it can be, a polynomial that goes on forward. So let's say that this actually goes on like this and like this, okay? Then the gain of this is actually, to be precise, the high gain, and it's the gain when z goes to infinity. Okay, so it's the value of the transfer function when z is going to infinity. So if z goes to infinity, all this part goes to 0 because you have z power minus 1, and so the gain here is defined as a divided c. Sorry. So a divided c is the gain, the I gain of this. So let's assume that the gain of c times p is much greater than 1. What the gain is telling us, if we compute the gain of all this transfer function, is telling us how much the disturbance is multiplied in the output. Okay, so the output, if the gain of this transfer function is 10, it means that the output is 10 times the disturbance. Okay, obviously what we want is that the gain of the transfer function is as small as possible. So what we assume here is that this gain of c times p is very large. If that's the case, then we see that 1 plus a very large gain is just the very large gain. The 1 doesn't play any role. And so then we can actually simplify p with p, and we get 1 over c of z as an approximation of the behavior of this transfer function here. So if now we compute the system error, okay, so the error here is r of z minus y of z, we obtain this expression. The reason is that r of z is equal to 0, okay, and y of z is given here once we multiply for d of z. So now let's assume that c of z has one pole at z equal to 1. So we define c of z in this way, okay, where c hat, okay, does not have any zeros. Okay, otherwise, if c hat has a 0, then it will simplify with the pole, and then it's not true that c of z has a pole in z equal to 1. So we have c of z that can be written in this way, in which c of z does not have any zeros. Then we consider a disturbance that is constant. So we consider a constant disturbance where the constant is equal to n. The transfer function, the z transform of this signal is given here. Now what we compute is the steady state error, okay? And we see what happens. So for the steady state error, we use the final value theorem, and we compute this. So this is very similar to what we have done for computing the steady state accuracy. We replace the value of u of z that we have found in the previous slide, that is minus 1 over c times d. Then we replace the value of c that we have given here, and the value of d that we have given here, and we obtain this expression over here. Now, since by assumption c hat of z does not have any 0 at z equal to 1, this expression is a fraction in which there is a 1 minus z power minus 1 at the numerator. When z goes to 1, this will be equal to 0. Okay? So what is that this slide is saying, what these two slides are saying? Basically saying that if we have a scheme like this, with this disturbance entering between the controller and the plant, if the gain of c times p is very large, and the controller has at least one pole at z equal to 1, then the steady state error due to the disturbance is 0. This information is very useful because we are designing the controller. So if we want to make a controller that makes the effect of the disturbance 0 on the output, we have to make a controller with two properties. One property is that the controller has to be of type 1, and the other property is that the gain of c has to be picked in such a way that c times p in gain is very large. Okay? Because if this is true, then the analysis that we have done is correct, and we have seen that the steady state error is 0. Obviously, this analysis works because we have assumed that r of z is equal to 0. If r of z is different from 0, then a new analysis has to be done, because obviously both the reference input and disturbance will contribute to the steady state error. So an interesting aspect that arises from this analysis is that the type of the system is not just important for when we are talking about the accuracy with respect to the input, but is obviously important also when we are talking about the accuracy with respect to disturbances, and in particular to make the disturbance not, to avoid that the disturbance affects our steady-state behavior. One important thing to point out is that it's very important where the disturbance is entering the system. If the disturbance does not enter here, then the analysis will be completely different. Let's see a couple of other cases. So in this case, the disturbance is entering after P and not before P. So there is no disturbance between the controller and the plant, but then there is a disturbance once that the plant produces a certain output, and the output that we actually measuring will be not the real output, but the output plus the disturbance. Now, if we compute y of z divided d of z, so the transfer function between y and the disturbance, the output and the disturbance, we will obtain this result, 1 over 1 plus c times p. Now, again, we see that if we want that the gain of this transfer function is as small as possible, then we want that the gain of c times p is as large as possible. If the gain is as large as possible, then the gain of the transfer function between y and the disturbance will go to 0. This is similar to what we obtained before. So again, we want the c times p as a large gain, but different from before, we actually don't need any condition on the poles of c. If the disturbance instead enters the feedback branch, so what we have changed here is just to move the disturbance from here to here, okay? So if we now compute the transfer function between the output and disturbance, since the disturbance does not enter just before the output, but actually enters after the output, the transfer function is completely different, and we obtain that the transfer function between the output and the disturbance is actually equal to this expression. Now we see a result that is quite very surprising. If we compute the gain of this, we see that to make this gain as small as possible, we have to take c times p with a gain as small as possible. So this is the opposite result that we obtained before. Because here, if the gain of c times p is as large as possible, we see that the gain of this transfer function will become 1. Okay? So the output will actually be influenced by disturbance. So to summarize, in our analysis of the effect of disturbances, we have to be very careful on which position of the feedback loop the disturbance is entering. Depending on the position, the steps that we have to take to reject or attenuate the disturbance will be very different, as we have shown in these slides. We conclude this lecture with this last slide, in which we point out a very important and surprising difference between continuous time systems and discrete time systems. In continuous time systems, the dynamic properties of the system basically depends only on the location of the poles, the closed loop poles in the S-plane. For discrete time systems, that's not enough. The position of the poles on the Z-plane is important, but is not the only feature to determine the behavior of the system. The reason is that the relation between the S-plane and the Z-plane is given by this expression, and we see that there is the sampling time appearing over here or over here. Okay? So this means that the sampling time has an important role in determining the dynamic properties of the system. To understand better what I mean, let's look at this example. Okay, so here we have two transfer functions. The pole of this transfer function is 1 over 2. So the sequence associated to the transfer function is 1 over 2 power k. And in this case, the pole is 1 over 4, so we have 1 over 4 power k. So what we may think is that, okay, this system for sure is going to 0 slower with respect to this system. So this is obvious, no? Because, I mean, it seems obvious because we have 1 over 2, then 1 over 4, and then is 1 over 8, and so on. In this other case, instead we have 1 over 4, and then we have 1 over 16, and then we have 1 over 64, and so on, okay? Obviously, this sequence is going to 0 much faster than this other sequence. However, we have to remember that these sequences are the result of a sampling operation. And also the sampling time plays a role. Because if we sample every 10 seconds, it means that from going to 1/4 to 1/16, we need 10 seconds. If this sampling instead happens every 0.1 seconds, it means that in 0.1 second we go here, and then so on. And by the time that we reach 10 seconds, we are much closer to 0 with respect to this case. So this is to say that the dynamic properties of discrete time systems do not depend only on the position of the poles in the z plane, but they depend also on the sampling time. And in particular, the settling time, that is one of the characteristics, one of the indicators that we have discussed when we were talking about the transient behavior, depends mostly on the sampling time. Finally, I want to point out that the closed-loop poles of discrete time systems are, in general, more sensitive to noise, to parameter variation, than those of continuous time systems. What does it mean? Well, this, again, is something that actually is quite obvious. In one case, in continuous time, okay, we have that all this region is the region of stability. So we have a half plane of good part of area where to put a pole. So if we have a pole here or we have a pole here, it doesn't change anything. Okay, the system is still asymptotically stable. In discrete time, instead, we have a tiny circle, okay, a circle of dimension of radius 1 that is good, and outside everything is bad. Obviously, this means that if there is an error and instead of having a pole here, we have a pole here, there is a huge difference, okay? So continuous time systems are in general more robust to parameter variations. Okay, and with this we conclude our lecture about performances.